Hey, it's Ryan. This is our first example dealing with forces and using FBDs to solve a problem. In this example, we are dragging our favorite crate full of fruit across a level, smooth surface. Something to note, whenever we say or read smooth in a problem, another word for that, or what that is indicating to us as physicists, is frictionless. If we apply a 157 Newton horizontal force, as shown, determine the acceleration of our crate. So whenever a problem says as shown like that, you're going to have been given or supplied some sort of drawing already. Or in my example problems, I often do that because I get to draw your picture for you. So here's our crate. And we could throw a couple pieces of fruit in there just for funsies. Maybe an apple. There we go. And that's being dragged along with a horizontal rope like that by someone kind of strange, just pulling a crate full of fruit, but whatever. So there you have it. If there's this large force on the crate and there's friction or no friction to oppose it, then we know there must be some acceleration in the direction of the force. And we're given a few things we can give our knowns. We know that the force we're applying is 157 newtons, and it's being applied through a rope. And so we're going to say that that's a tension force. The mass of our crate is 31 kilograms, and we don't know the acceleration. We also could note that the coefficient of friction, mu sub k, between the surface and the crate is 0, and that's given. So that would be the picture. Our job is to figure out the acceleration, but in order to do that, we're going to have to analyze the forces acting on the crate. And so we're going to draw a free body diagram. We're going to stick to those steps that we laid out for you in one of our previous videos. So we're going to do an FBD, and when we decide we're going to do a free body diagram, we need to decide what body we're actually separating from the environment. Well, we're really interested in the motion of our crate, and so we're going to do a free body diagram of the crate. So here's our crate. And now I would ask, what forces are acting on the crate? Well, of course, there's the tension force due to that rope that is being pulled. There it is. It's horizontal as given. The crate is sitting on the surface of the earth, so it has a weight force, weight. And you might remember that weight is always equal to mg, that's just given. There's no friction to speak of, but the crate isn't accelerating downward, is it? It's not going through the ground, it's sliding along a level surface. And so, of course, that surface is interacting with the surface of the crate in the form of a normal force. So we could say there's a normal force on the crate, and it opposes the weight force, keeping the crate from going into the earth. That may seem simple, but it's true, and we have to account for it. We're also going to choose a coordinate system, but before we do that, actually, I want to finish by drawing our acceleration vector. And notice my forces all are in contact with the body, but the acceleration is off a little bit separated. Now I'd like to choose a coordinate system, and it makes sense probably to just use a standard XY coordinate system. Anytime we want to work with a free body diagram like this, now we've covered all 4 of the first steps. The last step is to apply Newton's second law for the directions indicated by our coordinate system. So we have the sum of the forces in the y direction, That would equal ma in the y direction. And we have the sum of the forces in the x direction, and of course that's ma in the x direction. I'm going to drop vector notation here because we're splitting up the directions accordingly. Our acceleration is clearly horizontal. It's given in the problem. It's moving along a level ground, and then it's shown in the problem the direction of motion. So we can say that ay is 0. And now we just look at our picture to know what forces we have to add or subtract. In our picture, we have a y direction normal force and a y direction weight force. And in our picture, we have an upward facing normal force, which is the direction I've chosen to be positive for y, and a downward weight, which is negative. So I'm going to write normal minus weight equals 0. And this will just tell us that the normal equals the weight force, and weight is always mg. So we could determine that normal force if we wanted. The problem doesn't ask us for it, so why spend extra time? We know that A is in the x direction, so I'll write A for that. And there's only one force in the x direction, and it happens to be going in the positive right direction. So I can say tension is the sum of our forces. There's only one, and it equals ma. Now I can solve for A. A must be T over m. That means A is 157 newtons divided by 31 kilograms, and so A will equal 5.06 meters per second squared. But A is an acceleration, so that's not enough. We need to give the actual vector solution. So A vector is equal to 5.06 meters per second squared in the x direction. There are several ways to represent the x direction. I like to use I hat because it's usually the most common used in physics. You could also just write horizontally or in the x direction literally, and that would be okay. So that's a very straightforward example using a free body diagram to solve for an acceleration. The next example will have friction and an angled tension.